Good day everyone, good day sir. My name is Diana Roses Galbuena and my topic is all about Cantor's algebra of set, where we will explore about the class construction, its operation, and the Russell's paradox. The content of my topic is all about Cantor's algebra of sets, class construction axiom, class operation, and the Russell's paradox. First, we will tackle about the Cantor's algebra of sets. I have here a definition of terms where we have class inclusion, power class, and ordinal numbers. Class inclusion is all about the relationship between class. A class A is said to be included in class B if A is an element of B. While a power class denotes if a set A is a power set of A including A itself. It represents a set of all possible subsets of A. We have here A is a set containing the element of 5 and 6, where the power set of A is a set containing 5, 6, 5, 6, and an empty set. While the ordinal numbers, Cantor defined it as a class that well-ordered other classes providing basis for comparing sizes of sets. So the introduction of Cantor's algebra of set. Cantor's algebra of set, also known as the set theory, is a foundational branch of mathematics developed by the German mathematician Georg Cantor in the late 19th century. It deals with the study of sets, which are collections of objects or elements, and provides a framework for understanding their properties and relationship. The following are the overview of Cantor's algebra of sets. 1. Set definition, class operation, complement, set differences, Cartesian product, inclusion, and subsets, and also cardinality. So who is Georg Cantor? Georg Cantor, or Georg Ferdinand Ludwig Philipp Cantor, was a prominent German mathematician who is best known for his groundbreaking work in the field of set theory and the development of the concept of transfinite numbers. He was born on March 3, 1845 in St. Petersburg, Russia, into a family of Danish and Russian descent and passed away on January 6, 1918. Georg Cantor is universally recognized as the founder of modern set theory, who worked this theorem toward the end of the 19th century. His father was Borg Waldemar Cantor, who was a successful merchant, and his mother was Maria Anna Bohm, who was a talented musician. He came from a well-off and cultured family. Cantor held academic positions at various universities, including Halle, Würzburg, and Halle again, during his career. His groundbreaking work on set theory and the transfinite numbers emerged during this time at Halle. He completed a PhD in mathematics in 1867 at University of Berlin. His dissertation was on number theory, particularly on the properties of algebraic numbers. So speaking of Cantor's theorem, the cardinality of a set is strictly less than the cardinality of power set or collection of subsets. Cardinality of classes was introduced by Cantor. The concept of cardinality of sets defining different sizes based on bijection, also called as one-to-one correspondence. This concept extended to class, but infinite classes have varying cardinalities. So we have here a set of A is less than the power set of A. This is clear for finite set. No one had seriously considered this case for infinite set before the German mathematician Georg Cantor. In 1891, proof of Cantor's theorem for infinite set rested on a version of his so-called diagonalization argument. Diagonalization argument proves that set of real numbers is uncountable. Cantor's proof that the some infinite sets are larger than others. Example, the real numbers are larger than the integers. As we all know that real numbers consist of integers, rational, irrational, counting numbers, natural numbers, and whole numbers. while the integers consist of real numbers, but it only includes the positive and negative numbers and also the natural numbers. Further, Cantor's proof that the power set of any set, including any infinite set, is always larger than the original set lead to create an ever-increasing hierarchy of cardinal sets. This proved that the set of real numbers are uncountable. Cantor was able to prove that there is an increasing sequence of larger and larger infinite set, or should we say, infinitely many different infinities. Next, we have the class construction axiom. So, class construction axiom or axiom of separation is a concept in set theory, which is a branch of mathematical logic. It is one of the axioms used to define how set can be constructed and is a fundamental principle that allows the creation of subsets based on specific properties. It allows the formation of classes based on a defining property. It helps us defining classes without encountering the Russell's paradox. It is essentially stated that for any set A and any property of P of X, there exists a set B such that for every element of X is an element of A and P of X is true. In simpler terms, it allows us to form a new set B selecting elements from an existing set A based on the specific property P of X. If an element in A satisfies the property P of X, it becomes an element of the new set B. In illustration, imagine you have existing set A that contains the number from 1 to 10. A is a set containing 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10. Now, let's say we can create a new set B using the class construction axiom. We want to B containing only the even numbers from set A. The property P of X in this case is X is an even number. Using the class construction axiom, we can define set B as follows, where B is a set containing X is an element of A, such that X is even. Here how it works, we consider each element X in a set A. For each X, we check if X satisfies the property X is even. If it does, we include it in set B. If applying the process to all elements of A, we obtain set B as follows, where B is a set containing X is an element of A such that X is an even, or B is a set containing 2, 4, 6, 8, 10, which is an even numbers. So using the class construction axiom, we can construct a new set B that contains only the even numbers from the original set A. This clearly illustrates how the axiom allows us from the subset based on the specific properties. Next, using the class operations. So we have here the class operations, the union, intersection, difference, and also the complement. In union, C is a union of D is a set containing X such that X is an element of C and X is an element of D. All the elements in C and D will be combined, while in intersection, C is the intersection of C and D is a set containing X such that X is an element of C or X is an element of D. We only get the element where they have that appears in set C and D. We don't include those elements that doesn't appear in the other set. Next is the difference. The difference of C and D is a set containing X such that X is an element of C and X is not element of D. While in complement, we have the complement of A is a set containing X such that X is a set and X is not an element of A. All the the elements that appear, all the elements that doesn't appear in A is the set that it will contain. Next, we will have the Russell's paradox. So who is Russell? Who's Bertrand Russell? He is a British philosopher and mathematician born on May 1, 1872, Trelik, Monmouthshire, Wales, and was died on February 2, 1970. He was awarded and honored of Nobel Prize in 1950, a notable work for Principia Mathematica. Bertrand Russell was known for challenging foundation of mathematics by discovering the Russell's paradox. Russell's paradox, or paradox of Ernest Zermelo, is a statement that contradicts itself. It is true and untrue simultaneously. It was discovered by Bertrand Russell in 1901 and being published in 1111 by both Russell and Gottlob Frege. The Russell paradox, it defines a set A as a set containing all the sets that are not member of themselves in a problem or paradox. If this set A contains itself, something is wrong because it cannot contain itself. It is incomplete because set A contains all the sets that are not members of themselves. Symbolically speaking, R is a set containing X such that X is not an element of X. If R is not a member of itself, then its definition dictates that it must contain itself. But if it contains itself, then it contradicts its own definition as the set of all sets that are not members of themselves. Symbolically, altogether, let R is a set containing X such that X is not an element of X. Then R is an element of R if and only if R is not an element of R. Example, we have here the barber paradox. Suppose there is a town with just one barber who's a male. Every man in the town during exactly one of these things, shaving himself or going to the barber. In this town, every man keeps himself clean and shaven. Asking the question, who shaves the barber? This results in paradox. Both of the possibilities result in barber shaving himself, but this is not possible since he only shaved the men who do not shave themselves. So that is all of my report. Thank you.